tried not to blur my background, but I don't know what the Zoom decided to do that lesson. Okay, so now let's start, and we have a lot of material to cover today, but I'm quite sure that we can make it. So today evening there will be a reception hour, only WhatsApp questions, and at Sunday you can also schedule a meeting. So I think this should be quite okay. And if you need also a meeting or a Zoom, a short conversation today evening, it is also possible. Okay. And the reception hour will be permanent on Sunday. Okay, at the hour that I wrote you at 12 to 2. Okay. So during the course so far, we were talking about the idea of modeling the Poisson neuron and simulating it and so on. And now we're going just a bit into more details, into the wild world of models. So far we were just focusing only on one model of the Poisson neuron, and now we want to talk about something which is a bit more wider. For example, a model relating between a stimulus and a neural response, okay? So instead of just looking at the spike generator, so that you don't fully know why does it respond the way it responds, we want to look at the possible function over here, the encoding function, which relates to that the x-axis will be the stimulus, and the y-axis is a neuron response. And I do believe that many of you heard that today it is commonly expected that when you do this neuroscientific if you want to publish a neuroscientific paper, so there is a very high chance that you will be obligated to offer a model. And we want to speak about how to start to do it. So we will have a few classes just about this field of models. Okay? So what are you going to do in the lab when you want to create a model? So you first start with collecting the data, which is the experiment themselves and the techniques and methods from the field that you are studying. And then you go on to some pre-processing of the data, which is something that we speak about it not too much, but a bit. And then you want to say that you want to offer a kind of function and to optimize the parameters that they mentioned. So I want to give you an example. So in a paper that I'm working on, I'm studying the effects of microsaccades on the neural responses of V1 population, okay? And then I discovered that when I average across all the neural response in V1, I can see that I have two phases. So that I have it in 3 different monkeys. So that if the microsaccade starts over here, the response begins to decrease before the microsaccade, and then there is an increase in activity. And this biphasic modulation is the thing that I want to report about. So when I want to report about it, so the first thing that I do is that I take all my data, and then I average across different trials, different microsaccades, aligned responses, and so on. And then the next thing that I do is that I want to say something about this model. For example, instead of talking about the average of all neurons in all V1 across all possible microsaccades, I want to go into something into a higher resolution and to talk, for example, only about this biphasic modulation of only 500 neurons. So this is what you see here. I have this recording from a specific population in my data. And you can see that they have this biphasic response over here, right? And when I look at this biphasic response, I want to find a model that will describe this response. So what I thought about it, it's not something that they took from the literature. I thought about, okay, let's try to have a negative Gaussian for the negative part, and then have positive Gaussian for the positive part. And in between, I want to do something between these two things. And then I want to find the parameters for each of my pixels or for each of my neurons, which relates best to the activity, to the real activity over here. Okay? So in this class, what we are going to talk about is, first of all, how do you achieve this? Okay, the data itself, how do you average it? And we are going to talk about two directions of averaging and a correlation. And the next thing that we want to talk about is to have another example of a model, which is called the linear kernel model. That in this one, you don't need to think about the function and to try to find the parameters. You just have a given function, and you need to find a specific parameter, but the function is given. Okay, so I hope it was clear, but if it's not, we'll talk about it some more. Okay, so this is just, let's say, a viewpoint from the bird's eye on the subjects that we are now talking about. Okay? And of course, there is a main question of what is the advantage of models? Why do you think that we want models? Why do we need them? Great, extrapolation. And what do you mean by that?
You don't know exactly how something behaves. You can put it in the model and you expect what you do.
Great, so you can have a prediction. And why does this prediction help us? Why do we care about these predictions? Yes. Okay, so models are a bit less for statistical tests, but it is true that they are used for generalization. But why do we want it? What makes a model so applicative from a more applicative point of view? Yes. So we can either use it for decoding, and we can also interfere, right? So for example, if I can model a disease, if I can model a perception or something like that, or I can model how specific part in the brain works, I can also try to have a machine that will be related to this part, and I can give this machine my function, right? So there are a lot of advantages for the world of models. And as someone who comes from physics, I can tell you that all that you study in physics is only models in the first degree. You almost don't study anything that's statistics and collecting data and experiment, nothing, only about how to deal with models. And just study a lot and a lot and a lot of models. And when I first came to the field of neuroscience, I asked to myself, but wait, where are the models? So in neuroscience, you don't have a lot of models, but still you do have some. Okay, so we will have in the next in this recitation, I will talk about two types of models. And then in the next one, we'll talk more generally about optimization of models. And then I want to say that if we have this stimulus to neural recording, we have this function. So this function is called the encoding function. Therefore, f of s equals some neural response. And decoding is the reverse function, okay? F of neural response equals to specific stimulus, okay? So this is an example for encoding. So this, when I show you this figure, I just want to say that when you have a very basic neural experiment, a controlled one, how is it performed? So you have this animal, and it is seated or restricted in some way, animal or person or something like that. And then you just show him again and again some specific stimulus, for example, the stimuli which are presented here with different types of odorants. And then you have this neural recording over here. Okay, this is quite the basic framework of neuroscientific experiment. And when we look at that, we want to understand what do we do with the events of the stimuli? How should we look at them from a computational point of view? Do we take one point, or is it a duration? And today I want to talk about the two possible ways of locking on the stimulus. Okay, so I'll start with the easiest and most straightforward way, which is called PSTH. Okay, so PSTH is an acronym for a peristimulus time histogram, and I also call it average across trials. Okay, because this is what it is. It's very, very simple. Okay, so you have here, for example, a recording. Okay. So you have a recording from a neuron, and you can see here the stimulus marker in red. And then you have different trials. Some of them have these spike lengths even before the stimulus marker, some of them after. In some of them, the stimulus is straight at the beginning. In some of them, it's a bit later. Okay. And PSTH is that you take all these markers and you just align them. You crop these vectors of trials. You align all the stimuli to be one after the other. And then you pin the spike numbers within each one. And you can calculate the average neural response. Okay, it's really, really simple. Is that clear? Great. So this is the PSTH. And of course, there is some information missing in PSTH. And what is this information that we cannot really know, only from the average? What is missing? Okay, so let's say that you write n equals 10, but you're in the right direction. Why did you say number of trials? About what is going on within each one of them, right? Maybe, for example, there was only one trial that responded, while the others didn't respond at all. And then when we average, we have only the average of practically only one trial, not across all the different. So for this reason, we don't use only PSTH. We also use the raster plot. Okay, so you can see here. Also in your project, you are asked also to plot the raster plot. And then you can see that there is a clear relation between the PSTH here and the raster plot that we see here. And in the raster plot, each row is just a different color. It's the same, but only with a row data. Okay? Very simple, I think. Okay, so now, so right, so we were talking about the variance, so that you can see it only in the raster plot. And, okay. Yes. So I think that you don't want to, my point of view is that you don't want to lose information when you average across the different trials. So I wouldn't take a very, Julia, you are asking, right, about the size of these fields. How do I decide? So I think that if you can stay in the highest resolution as possible, I would stay at this resolution. And only then, after I average, if I want to clean to have a better SNR, only then I would use a convolution. Okay, but I wouldn't start by cleaning that bigger sizes. Okay, but I know that it might be, maybe it's because it is written here, that you can also have a bigger size. Yeah, so I would keep the same resolution time as any of the single trials. Okay. And the reason for that is that if it is robust in your single trials, it should be also robust in the average. Okay, so I would rather keep it as closer and as undisturbed in relation to the raw data. This is my point of view anyway. Right. Yeah. So also, but in the convolution, it's across only one trial. This is the difference. Oh, and PSTH, by the way, another important thing about it is that you don't calculate the firing rate constant for each trial, and then you average between them. You only make this histogram like here, that if you count the number of spikes within each pin, and then, for example, you can smooth it. Okay, so you keep it as raw as possible. Great. And maybe Zal talk to you about JPSTH, and I won't talk about it because it's one of the things that were for me. I took it off because of the short duration of the semester. But if you want to speak about it, we can talk about it in another opportunity. So PSTH, I think it's quite a simple way that you have again and again stimulus, and then just align it to the stimulus onset, right? Now the STA, it's one of the methods in the family of reverse correlation. Therefore, instead of doing the more simple thing, going from stimulus to the neural recording, in the SDN, we're doing the reverse. We are going from the neural recording to the stimulus. And by so, we believe that this will help us to explore or to find what is the best stimulus for a neuron. Okay? So let's see here. There is a very nice illustration that I like to show, and it's this one. So if you have two recordings, stimulus and a spike protein. So I've been asked what kind of stimuli like that. So it could either be at the level of the neuron that you have the current and you have just a current which changes in time. Or at the previous lesson, someone gave me an example that if you have voice or you have an auditory stimulus, then this auditory stimulus can just change in time, right? And then you can record the spikes from the auditory cortex or whatsoever. And then, for example, you want to ask yourself, in this type of stimulus, what is the receptive field of the neuron, right? Maybe you remember from the neurobiology classes that when we talk about receptive field, you remember what it means in the visual system? It's a bit easier that if I have this visual field like this, so I'm fixating over here. So there will be a response in one neuron in relation to this point, and for another in relation to this point, right? Now in the auditory cortex, it's not on the visual field. It's between different cues, between different frequencies. So let's say, for example, that I want to discover what is the preferred frequency for this neuron. So I just put an auditory stimulus with different possible ranges of tones and so on. Just put it on, okay? And then how can I discover what is its preferred stimulus? So the idea behind STA is that I will take each of the spikes and then I'll align the stimulus to the spikes. Do you understand the difference? In the PSTH, I align the neural response to the stimulus. And here I'm doing the reverse one. I'm aligning the stimulus to the spikes. So I'm looking at the spikes and I'm asking myself what happened before and after the spike. Okay, so for example, here you have this spike in red, and you cut its vector from the stimulus and you put it here. Okay, and then there is another one in green over here. So you cut this part and you put it here. Okay, and how do you decide about the size of the vector that you want to cut? So it depends on prior knowledge. For example, you don't want to have too many overlaps. You don't want to take, for example, around this part, you don't want to take this size of the vector, right? Although they did it here, but I would already cut it before, because you don't want to mix responses to other spikes before or after. And so this is about the duration. And then when you have all of them, the next thing that you do is that you average. Okay, and then you have the STA. Okay. So what type of data is this in here? I would reduce 2 points to a student that can submit such an answer for STA. Yes. Right, and also, yes. Okay, so it's the axis, yes, and what else? Excuse me? Right, let's say that all of them are here, but still, what is missing? The variance, right? So let's say that I have a difference between a response average that looks like this, and its variance is like this, and another one that its variance is like this. Because in this case, it might mean that the average is either not strong enough because there is not enough statistical power, or another possibility is that the average does not reflect the stimulus preferred, the preferred stimulus on the neuron, right? Because there were too many kinds of stimuli with different quality. So always bring the variance whenever you average. Yes.
Well, when we say that STA is a type of reverse correlation, we're not actually doing the cross correlation between spouse and stimulus.
Right.
A way of calling it, it's a misnomer.
Yeah. It's not a cross correlation. You're right. It's more about the reverse and less the correlation. Yes. I like to show not the standard deviation. I like to show the normalized standard deviation, which is the STM, and this is the STD divided by square root of n minus 1, while n is the number of samples that you use for the average. I like to show this one, and the reason I like to show it is that you can see graphically the signification. In standard deviation, you can't always see whether this response is significant in relation to baseline or to shuffle or whatsoever. You understand? Because STD is dependent on the size of the sample. But the normalized one, you can already see graphically if the two, if they are not overlapping, and then it is commonly indicating that they are significantly different. Although this is not true, I just had a film like this for the past 2 weeks that I thought that two distributions are significantly different, but they were not, and I didn't understand how could that be, because the SEM really shows that they are not overlapping, and the reason was that the median was also almost the same, and the mean not. But it was like a nice lesson in statistics. A nice and bad one. Yes.
Does the need for the standard error also apply for the PSTH with the error bars?
Yeah, but you can either use the raster plot because it will present the same, right? Okay. So, and now I have another question. So we said that we are using the PSTH to discover what is the preferred stimulus on this neuron. What is the preferred stimulus? Yes, do you? Okay, so there are 3 possibilities, right? There is one possibility that the neuron responds to the decrease in activity. Another one, the decrease and which is followed by an increase. And another one that it is only for the increase. And which one is the right one? Did you understand the 3 possibilities? Okay. So if we have this STA, I'll write it on the board. So we know that when we have, so the neuron responds here, okay? So there is one possibility that this is a response to the trough over here. Another one is that this is the response to the trough followed by the increase, right? Trough plus increase. And another one is that it responds to the peak, only to this one. So which one is the right one? How do we decide? So is this neuron preferred stimulus is the trough followed by the increase, or the peak? Which one? Yes.
Theoretically, if you design it correctly, then like if it's responding to either like 1 or 3, no, yeah, if it's responding either to 1 or 3, the other one is going to be a flat line. Like in my mind is like, yeah, if it's only responding to the peak, then when you have enough of variation in things that you showed, then it would be a flat line up until the peak. And then if it's only responding to the trough, same thing, that it wouldn't show.
Okay, so you're saying, let's assume that most of these troughs could also go back to baseline, right? And then if it would respond only to the trough, then we wouldn't see this increase. So I believe that the reason that there is the probability of both decrease and the increase after is lower than just a decrease, right? But you didn't check it, you just assumed it. So the good thing to do now is to check it. Check whether after most of the troughs, is there also an increase, and whether troughs followed by increase are more probable to have spikes or not. Did you understand what I just said? Right. So this is one way to look at it. And another one could say, okay, I know where I'm recording from. If I'm recording from V1, for example, V1 has 50 milliseconds delay from the retina. Or the auditory cortex has about 20 milliseconds delay. So there is no chance that it responds to something that was less than 50 milliseconds. So it responds to the trough. And another one might say, but you are recording from the motor cortex. So this one precedes an action. Therefore, it does not respond to something that was before, but rather to something that will occur either now or after. So for example, it might be to responding to the prompt. So I'm telling you all of this because although this is a nice and very cool way to do things, it still does not mean that it tells us about what does the neuron respond to. Okay, and we need to keep that in mind. Okay, so let's have a question which is given from Izar exam. So we have these fairy 7 sense receptors which respond to the appearance of fairy dust. And this is measured in millimagic units according to the following reverse correlation. And we ask ourselves which of the following input will lead to maximal changes in the neural activity. Yes. Please tell me how to answer. So this is the reverse correlation is the STA. Okay, just to be sure, did you understand how to calculate the STA? Because you have it in the project. Was that clear? That you take the spike and then you go to the stimulus and the lining and then you plot it and you have the matrix and you average and show the variance. Next. So let's say that you have this average. So now you want to stimulate this neuron. What would be the best way to stimulate? So first of all, please tell me what are impossible answers. Right, because we see that it responded to something which is not constant, therefore we don't do treatment of A. Yes, others? What are the difference between DNC and DND? Right, and what does the 100 plus represent? Great. This is also called the DC sheet, right? Because this is the average of the response. And over here it's 0. Therefore, D and E are out of question. Okay, so we are left with the two confusing answers for either B or C. What are the differences between B and C? Great. Who remembers the formula for the relation between frequency and period duration? Right. Frequency is 1 over t if you look at seconds. Therefore, 1000 over t if you look at milliseconds, as in the y-axis over here. So, if we have 25 hertz frequency, this equals to 1000 over t. Therefore, t is 40 milliseconds, right? And if it's 50, then t is 20 milliseconds. Which one is the period duration in our example? The 20 or the 40? Right, why? Please note that this is one of the things that students are always confused about. So why is it 40 and not 20? Yes, so you need to have a full period. And a full period is composed both from the trough and from the peak. Because most students, the most common confusion is that they look only at, for example, only at this trough. And they say, okay, this is 20 milliseconds, therefore it's the 50. But no, a full period should be both the trough and the peak. Yes. Okay, so it's a good question, but in the exam you are given with a possible number of inputs. It is true that also in this kind of inputs there is also this they go back to 0, and here it doesn't, right? But also look, there is also another difference, that the amplitude, right? So over here the amplitude is 100, while here it's only 1. So you just need to pick which one is the most relevant and most close to the data that you're looking at. Yes, the one with the 25 hertz. Section, subsection, answer. Okay.
I'm
And-
sorry, can you explain please one more, why it's B?
Yes, so after we ruled out A, D, and E, was that clear, Ksenia?
No.
Okay, so A is irrelevant because the STA is not flat. And in
Okay.
B and E, we have this 100 DC shift.
Mhm.
Therefore, in D and E, it should fluctuate around 100 and not around 0, right?
Okay, yes.
So now we need to decide whether it's B or C. So we take them both and then we calculate the period duration. And in
Okay.
B, the period is 40, and in C, it's 50. And the period is 40 milliseconds in this wave because it has to be a full period is composed both from the trough and the peak. So this is why answer B is the right one.
Okay, thank you.
You're welcome. Great. So there are a few irrelevant parts in the answer to make you more confused. Okay, so the 100 has nothing to be, you don't need to consider it Not because it is irrelevant, only because in this question, it is irrelevant. In another one, it might be relevant. For example, if you have 100 or 1, right?
It would be one.
Then it would be 1 because this one is small.
And what is the name of the shift that goes with the 100 plus?
It is called a DC shift. Yes, because when we talk about current, is there a rock lover over here? Would you like AC DC? So you have DC plus AC, direct current and alternating current, right? So the DC is always the direct, where the flat line is, and the alternating one is the sine wave and the frequency of it. So it is very common that when we talk about recordings, we talk about DC shift. Yes, Sophie. Where? Yeah,
And
this
here,
time.
so here, small t is, oh, it's because it's triangle,
Yes, and it's also here small.
and this,
Ah, this is, oh, sorry. This is the period duration. It's a different variable. The small t is at specific millisecond, and the t is the size of this period. Okay? We'll have some more about it when we talk about the frequency domain. But this will take some time. It will be within three weeks or so. Okay. So, do you need a break, by the way? 5 minutes break? Because this might be a good time if you want. Okay, so take 5 minutes break, and at 5 minutes to 3, I'll go on. You are so tired, right? You didn't sleep before the submission of the first project or something like that? Okay. Where? Okay. So this is so it's good that this week is a bit more simple and a bit more relaxed. I think, right? This is much easier. Yeah, but in project 2, the first question is the hardest. And then I know that it really scared you, this GLM thing, okay? We are not doing the full GLM, we are just taking a model and we're trying to optimize it to a model. And it's not optimization, okay? It's not really that hard. Well, it's learned within a minute how to do it, but you can, all of you can do it by Sunday. It is much more easier than the previous one. Yes.
No, actually, it was just like, oh, I can take this 5 minutes because the previous exercise, I was like, how do you know that it's this, that we have to do this? Like,
Yes.
because you see, oh, I can recognize the frequency based
Right.
on the graph. So,
So the frequency is given inside the sine function, right? So this is the difference between this one and this one.
okay, so it's
So-
just like, based on the graph, you can say that the frequency is 40.
Yes.
And then we use what is inside the sine function.
Yes.
Because what is the equation normally inside the function is t, no. I know
So
frequency
it's
is.
always omega t,
Okay.
and this is multiplied by 2 pi because this is t.
Yeah.
It's a sine.
Because it's like, we don't know the frequency, but we
And it
know
could also
the
be
time.
2 pi over t multiplied by t.
Okay, or frequency time t.
Yes.
Okay, so 25 and 50 is a question of frequency. We take it and then we calculate the VT, I forgot the name of it.
Yeah, this period. I can, please, remind me to send you like kind of this, nice illustration, a wave that you have in waves, and you have, this is the T, right? And you have the length, this is the lambda. This kind of, we don't have it.
But it's not the same.
T is the time between, for us, it's the same.
Okay. In which?
In physics, you have, you can have either the wavelength, which is really the length between the two peaks, or you can have the time until you have a full period, and they might be different from each other, because, for example, you can have this wave and it moves slow, and the same one moves like this, right? Let's say that you float, okay, leave it out, it's the same. It's the
No,
same.
it's just like I don't imagine how it's possible that the period is not the same than that.
In you can say that it's kind of a multiplication of two. Leave it alone. It's in one dimension, and we have only t. Sorry. Right. Yes. It is called reverse correlation, but it is more about the fact that it is reverse, but you don't perform any correlation, right? You're just averaging. So this is a bit misleading definition. Great, okay. So let's go on. And I just want to say something that we will talk about more in the next recitation, that I will talk a bit about decoding. And when you have a decoder and you have a model, you want to know how good is your model, and you want to optimize it, and therefore one of the easiest way to do it is to use RNSC, but most of you should remember it from deep networks, right? Because you wanted to minimize the error, and this is the equation for the error. Okay, so I'm just showing you here, for example, that if you have this data, this is the real data, and then you have this function, which is the optimized function to describe the data as linear, right? How do you know it is optimized? It's because you calculate the RMSC of each one of them between the point and the function and prediction, and then you try to find the minimum. And you can see that even if you have a standard deviation of the measurements within each point, you can still calculate it. Great, so you know that. And another small definition is regarding what do we mean when we talk about linear models. So in the notes, I wrote about nonlinearity, but then I understood that Isao didn't teach you that, right? So we won't talk about nonlinearity, and if there is a question in the project, so please tell me, so I will take it off. Okay, but I just want to say that when we say linear model, what we mean is that we have a linear combination between scalars and vectors. Okay, and this is what it means that we have a linear model, so that we can the reason we are talking about that is the way that we optimize, we find these parameters, we find them in a different way when it is a linear model, and we have another way to find them when it is a nonlinear model. For example, like here, this is a nonlinear model, and in this type of model, we have these two variables over here, and we cannot optimize them based on how we do it in deep networks and all these theoretical ideas. So we optimize them differently, define them differently, okay? By simulations and so on. So basically, I'll start from here. commonly when we create a general linear model, I don't want to talk about what are GLMs and how we use them and so on, but the basic thing that we do in our science is that we first optimize to a linear model, okay? And then we add the nonlinearity of this model, okay? And then this one, when we have the spike generator, given this static nonlinearity, we can generate the spikes from the function of the rate, right? Like you are doing in project 2 in the Poisson simulation, and then you have this response. So we were learning a lot about this part of the spike generator, and in this recitation I want to talk about this, but I'll focus only on this. Just keep in mind that in most of the real world problems, we also have this static nonlinearity at some point. Okay, great. So I'll go back to the STA that we had here, and I'll ask you a question. Is the STA is relating between the stimulus to the neuron or between the neuron to the stimulus? What is the, let's say, the function of the STA? What is the input and what is the output? Yes. Right. So we are going on the decoding direction, right? But we are doing STA not in order to decode our neural data, because it doesn't really decode, it just tells us a preference of the neuron. We want to use it for encoding our data. So we want to take the result that we had here on this direction, and now we want to go back to this one to create a function over here. So we have a model that is called linear kernels. And this says the following. It says that the neuron response is given by the baseline response plus a function convolved with the stimulus. Okay? So each neuron has its own baseline response, and if you show a stimulus, you can multiply it or convolve it with another function, right? And then when they are convolved, you have the prediction of the rate. Okay, is that clear so far? Okay, so here we have this definition of convolution. You can either write it like this, or you can use the integral like this. So far, so good? So if we have this model, therefore, what we want to find for each neuron, it is linear kernel. Okay? So how do we do it? So I want to remind you that in the STA, I told you and nobody asked me, and I'm a bit curious about that. How do I decide what to show to the neuron? Okay, so I have this continuous stimulus. But how do I decide what to show? So in our model, they say don't show just any stimulus, a natural voice or something like that. You need to show something which you can explain mathematically. So what you're showing to this auditory neuron, you're presenting with a white noise. Do you know what white noise is? Does someone remember? What are the features of white noise? Okay, do you know how do you create the white noise? It's okay, yes.
Kind of a Poisson distribution, that's random independent sample.
It is in a way random, but the thing that you do to create a random noise is you take all possible frequencies, each one with a different phase, and you just sum all of them together. So when we hear a white noise, we hear all possible frequencies within sound. And as far as I remember, a chirp, this one, also has all the possible frequencies. If I remember right, I need to ask Ed because I think that he taught me that when you want to study the auditory cortex, you present this kind of sounds. So they are kind of chirping sounds. Okay, so now we designed another experiment, and in this experiment we don't take the stimulus that we are studying, but rather a new stimulus, a mathematical one that will help us to find the linear term. And now how we are calculating this linear kernel. So our model says that the linear kernel equals to the average rate during this experiment of the white noise, multiplied by the STA on the white noise data, and all of which is divided by the variance of the white. Okay? Is that clear? Yes.
We got we are supposed to use STA from same data set from another experiment that we run before. Like in the project, for example, where we do
Right.
different data sets.
So in the I'm maybe there is a misleading guidance in the project, but when you are calculating the linear kernel, you need to do the STA on the white noise. Okay, and not on the given data of the STA. Okay. Yes. Yes.
Okay.
Yes. Yes. Yes.
Is so for R, is that for a specific time point or window, or is that just the average?
Average, firing rate, all the rules, yes. Okay. Average rate across all of the samples. All of the recording. Okay,
That's of your data.
yes. And if there is a misleading guidance in the project, please write me so I can note everyone and also upload a new file. Okay, sorry for all the mistakes. Yes. The STA is for the white noise, yes. It's in relation to the white noise, yes. And the reason we are doing it on the white noise, again, when we think about the auditory system, is that white noise has all of the possible frequencies. Therefore, you believe that your STA will allow you to find the specific frequency in relation to this neuron, because you are presenting all of the possible frequencies. So it should respond only to the relevant ones. Okay. There are a few assumptions that I feel that you kind of understand about STA, that you, for example, there are a lot of questions whether you can use STA just in relation to a spike, right? Because we know that spike does not carry all the information. So why should we align it to spikes? So there are some works that show that you don't need to align it to the spike, but rather to the change in the firing rate and so on. But the basic idea of this reverse correlation is the same. It's just a question on how you align it. Yes.
So for the project, we're in general, we just randomly pick a spike.
Yes.
Okay.
All the possible spikes. And then you, yes, for each spike, you crop the stimulus data and then you average this matrix. And if the stimulus is not long enough, you just add nuns before or after. Yes.
Project, it asks us to use different size windows. Is that the window size of the STA then?
I don't fully remember, but I think
Because for one part, we use from negative 500.
from 100 to 3000, right?
Yeah. Is that-
I think it's for the STA, but please remind me this evening in the reception hour, okay? I'll double check it. Yes.
You said that we don't have, don't have the for adapter. How do we decide if it's not?
No, now we are looking only at the linear. This is here, this is called a linear equation because you have the stimulus, it is convolved with a kernel, and you add something linear to it. So this is called the linear model. And afterwards, after you find this linear kernel, you can multiply all of these by a nonlinear one. For example, random that you are familiar very closely. Yes.
It makes sense to include the time points also after this spike for the window be restricted to only the points before.
No, commonly you take also almost 100 milliseconds after.
So, like what,
No, you can say you can take something longer before 300 milliseconds before 100 after until you find the right one that gives you the best SNR.
so it's
No, there is no strict rule. It depends on the neuron. In the motor system, for example, I would use something which gives more for after. Okay, so anyway, this equation, I think now it's more clear what you need to do, and then you can see what does this linear kernel create. So if you have this stimulus over here, and then you have this spike trend over here, and from the spike trends, you calculate the PSTH, which is here in the gray. You almost don't see it, but this is the average firing rate. And then we want to ask yourself, if I will take the stimulus and put it inside my model, what would my model predict? And then you can see that this is the prediction of the model, and it is not a very bad one. Okay, so this is like an example for a model for encoding. So that we want to predict the neural response, and we have a cute and nice way to do it. Okay? Great, and these are some examples that you want to add some saturation because the neuron cannot fire more than possible or something like that, or that you want to rectify it, or you want to add an hyperbola or something like that, right? And hyperbola is like adding some probability to specific firing rate, which might be more probable or something like that. So here we go again, that in the project you have to create this linear filter, but in real life you sometimes add the status nonlinearity to represent the non-phenomenal saturation and so on. And then when you have the firing rate function, you can generate the spikes, and then you can relate it with, you have a function which predicts for each stimulus its response. Okay, cute, huh? Ta-da! Okay, so we have about 20 minutes just for the last subject. So please gather yourself. This is a simple subject, and it will be also in your quiz within 10 days from now. Okay, right? 10 days? Yeah, something like that. But Monday, the 10th of June. A bit more, yes. Don't panic. Okay. I for the project, so I offered you that you can submit only 2 out of 3 questions. I highly recommend to submit the first 2. And the other one you can submit during the whole week. And if someone says that it's really hard for me also to submit the project and to get ready for the exam, I will allow in very, very special cases to submit the last question even after the quiz. But it won't be good for you because the questions are quite helpful. But you can choose which are the 2 questions that you want to submit. So if you prefer, for example, to submit first the second and the third question, you can do that.
I just. And well.
Is that quiz or mine? Ah, okay. I gave it until, yeah, it's okay. Just solve it whenever you feel it. Okay, during the next week. Okay, look, I heard that this is a very rough semester for everyone. So therefore, we decided to do some changes in relation to previous years. So that these recitation quizzes are for you and for me. So if someone doesn't answer, if only one doesn't answer, or if you really can't make it on time and so on, it's okay. So just relax. If you need a special occasion just not to submit at all this week, you can write me an email and you can have 2 like this and you will just have 2 free points in this very, very hard course, okay? So just don't worry, be happy. Great. Okay, so in the next recitation, I want to speak about decoding. But before I speak about decoding, I can say that decoding is like trying to create a full function like we did for encoding. But when given a normal recording to predict what was the stimulus, this is kind of mind-reading, right? This is what decoding means. But practically, most of the papers about decoding are practically about discrimination. And what does that mean? That when you have a decoder, you could have every possible neural response and predict any possible stimulus, right? But when there is discrimination, you say, okay, I know that there were specific possible stimuli. For example, it was either a turtle or a bug that my neuron responded to. And now I need to choose which one is the more probable one, right? And for this, we need to go into some statistics. And maybe remember that in statistics, you had possible tests to decide how 2 distributions are significantly discriminative from each other. This is quite a hard word to say, discriminative. Okay, so maybe remember you have in statistics, you have either the t-test, right? That you look at your samples in relation to their average. And this is a 1 sample, and this is a 2 sample t-test. And you can have, for example, Wilcoxon sign rank or rank sum test, which looks, for example, in relation to the median. And it does not assume that it is a Gaussian or a normal distribution. Okay, so this is for statistics, and maybe you remember it, and maybe not, and it's okay. But maybe some of you are familiar with the idea of D prime. Do you know the idea of B prime? Would someone like to explain to us what B prime is? No, really? Okay, did you ever hear? Right, before today, did you ever hear about its quantification? So it's more common in psychology, I think. So can you say a word about it, Sophie? Whatever you remember, feel free.
No, but I think I can just say what we heard this morning, so.
Okay. So D prime represents how two distribution means are far from each other, okay? And the way that we calculate D prime is that we take a specific axis and we call it the Z. And then we say, let's say this is a test that we have given to people with possible coronavirus, okay? And then we want to say, if you get a specific level of, I don't know how the corona works, but let's say that if you have a specific number of ROCs of this and this in your map, so this is a higher, so that means that you are sick, or if you have under, it means that you are not sick, right? So, you know, when you have this corona at home that you check, you take it inside your mouth and so on. And these two lines, they represent a level of, I don't know, germs, or I really don't know. Okay? So we can say that if you have this level, so that means that you belong here, you are in the sick population and you need to stay home. And if you have less than that, that means that you are not sick and you don't have to be quarantined, right? Yes.
Yeah,
Excuse me, there.
define.
Yes. I finished now. It's only the relation between the heats and the force. As far as I remember. Okay, so now we want to take this idea that we said, let's have a specific threshold. Everything in the right to this threshold will be positive and everything on the left will be negative. And now we can say, but how did you choose this threshold, right? So now we go on from V prime, which someone can say, I looked at the biological mechanisms of our corona works and so on, and we can now go to something else, which is ROC. And ROC says, I don't know where the Z should be, but I can calculate for each Z how mistaken it is. Okay? Did you understand what I just said? Okay. So who said that the Z for determining if someone is sick with corona is here, or should it be more left? Who decided? The scientists, which are both to you. How did they decide that?
What is it?
This is the Z here. This is the pressure.
The C.
Yes. This means that there was a specific 10 germs in your mouth which are related with corona, and this means that you are positive for corona. But who said that this is the right place to put this in, the Z line? Yes. For example, exactly. So great. So you are saying people can come up and say a lot of possible assumptions about it, but then you can say, okay, let's, instead of looking at specific Z, let's look at all possibles. And the Z could be here, or here, and here, or here. And if the two distributions are fully independent, For example, if one distribution is here and another is here. Okay, so if I take the Z here, here, or here, it will be the same, right? Because it doesn't matter where did I take this line that's saying this belongs to this distribution and this belongs to this, right? But if they are the same, so if I'll take this one, and this one, I'll be mistaken at the same level. So we can say that we can have this ROC, this ROC curve. It is based on this idea that I can move the Z, and if the two distributions are basically unequal, I can take almost every Z and I will be right. Okay? Yes.
I'm not clear on what two distributions we're comparing here.
If you are sick with corona or not. The probability of that, okay, given the number of germs that you have in your mouth in this A, what is the probability that you are sick with corona and what is the probability that you are not?
Okay.
So if you have 3 germs, you're probably not. If you have 10, you're probably yes. And the probabilities are given by this y-axis. Was that more clear?
So they're not complementary in this case?
No.
Okay.
For example. It could be 2 syndromes, it could be 2 types of stimuli that were presented, everything could be. Okay? Yes, Julia.
That would be non-money.
Yeah. So the nice thing about ROC is that you don't have to assume normality. This is one of the best thing about it. You don't have to assume anything. You just ask yourself, are these two distributions are discriminative or not? But you are right that when you use the prime, we have to assume that these are normal distributions. You are right. Okay. So we'll see in a minute. I'll show you an example. So now what we are going to do, so we have these two distributions, and this is the null hypothesis, i.e. I'm not sick, and the positive, the alternative hypothesis, I am sick. And these are the two possible types of errors that we might have. In one of them, for example, I did the corona check, and then I was mistakenly considered as sick with corona, although I am not. And this is called the alpha, okay? And this is false detection. So I did have a specific number of germs in my mouth, but I was not sick, and therefore it was false. So this is a false positive. And the other types of errors is the false negative, that I was sick with the corona, but I had less number of germs in my mouth than is considered as sick, but I am sick, and this is called the beta errors, okay? And this is false negative. Okay, so now what we want to do in the ROC is each time we will look only at the right side of the ROC, and then we will calculate the relation between the H1 and the alpha errors, okay? And as the relation between them is more big, therefore these two distributions are more discriminative. Okay, so let's see an example. So we have here all the, please note all these definitions that you have here, because I think that in your project you are asked about the sensitivity or something like that. So just take it from here. So I want to show you an example. Oh, and I wanted to say that this is how ROC curve looks like. So the more it is closer to this region, that you have the relation between the false positive and the true positive, the more it is close to 1, then the two distributions are more discriminative, and as it is closer to the middle half, there are less, okay? So many times, for example, when I use the ROC, I don't really calculate the ROC itself. I just calculate the area under the ROC. And I don't need to go all through these plots, okay? So I'm looking, I'll show you here, okay? So this is an example from an exam, and I think this is one of my favorite examples because this one is very clear. Oh, and by the way, we need to finish. Is it okay that I take another 5 to 10 minutes? Can you make it? You are amazing. I love you. Okay, so let's say that we have this neuron over here, and this neuron either responds to a prey or to a predator. If you remember, in project 1 that we submitted, you had these neurons which are responding to different numbers of fingers, right? And then you were given with a neural response, and you had to decode to guess what was the number of fingers. So this is exactly what we're doing now. We're saying how probable it is that it was 2 or 3. Okay? So, and this is what you're going to do in this project. You're going to use the ROC exactly for this kind of decode. Okay, so the neuron could either respond with 0, 10, 20, 30, or 40 spikes per second. And if it responds with 0, it would be either to a prey or predator with a higher probability to predator. If it's 10 spikes per second, it's 0.2 for prey and 0.3 for predator. And if we are at 20, it's the same between the two of them. And here they are getting opposite. It's a higher probability for the prey. And here, if it's fires at 40, it could be only prey. And then we are asked to plot the ROC curves, okay? The first one is for the neuron, and the second one is for the behavior. And the behavior is given by a specific function, okay? So in the behavior, we, instead of having this, we can just write a table that, for example, okay, we'll see in a minute. Okay. Okay. So how do we calculate the ROC? So we are given with the two distributions. And now we want to put all possible Z lines to decide if we, and the Z line, I remind you, it says if on my right it is the positive, or on my left is the negative, okay? So if I have, let's take as this one, and I'll put this. I don't know if you see the numbers, I'll write them in a second. Okay, so here we have 0.3, 0.2, and that's it. This is 0, and this is 0, 10, 20, 30, and 40. Okay? So if I take this Z and I put it here, how much from the blue distribution is on my right? How many percentage? 100. Therefore, the true positive is for Z equals 0, the true positive is 1. And the false positive, how how many of the left distribution did I put mistakenly inside the right distribution? Also 100. Great. Let's try the next one. Now I'll put the Z over here. How much of my blue distribution is on my right? From here on, let's say I will always count also, maybe like this, but it should be like this. How much of the blue is on my right? Again, 100. So on 10, I'm still at 100. And how much of the red did I mistakenly put in the wrong distribution? Excuse me? I think they heard right. I was just not sure. So here, these are 30% out. They should be on the left, but 70% are mistakenly on the right. So it's 0.7. Would you like to try another one? Okay, so now I'll do another one like this. And Z equals 20. So how much of the blue is on my right? Right, because I missed this part over here. I mistakenly took it out. So now I'm left only with 80%. And how much is on my right mistakenly from the red? So now I have 40, right? Okay? So now I took the Z and then I took it at each possible value. Yeah, from this one, at true positive, I look at the blue because this is the one on the right on my Z. And in the blue, I didn't take all of the distribution. I took only what is 25 per second and higher, right? This is the blue over here. So this one, I don't look at it. So I have only 0.8 from all possible distributions, all possible events. Yes.
Just the blue means, or what you're saying for true positive is we think that it's from the prey distribution, it's prey,
Yes.
and it is, and the red is, we predict that it's a prey, but it's a predator.
Very good.
Okay.
So I say, if I put the line to say that the blue distribution is on the right and the red is on the left, how wrong I am regarding to the left, and how right I am regarding to the blue. Was that clear? Do you want another one just to be sure? Okay, let's have this one. If I say everything on my right from the neural response in 30 spikes per second, and therefore I conclude that this is a prey. How true I am? At what percentage I am true? Prey is true. Right, it's 0.6, right? And how wrong I am? Is there any chance that it was a predator? Yes. What chance is it? 0.2. Was that clear? Because this is this part. And at 40, I have left only with 0.3 from the blue and nothing from the red. Okay? And now we can take the neuron and create an ROC for the neuron. Right? And this is what we just created. And now we can calculate the ROC of the behavior. The ROC of the behavior is given by a function that says that the true positive is the square root of the false positive. Okay, so we can create something like this. And then we can and here, we can plot. The x-axis means the false positive, and the y-axis the true positive. And which one is better? The neuron or the behavior? The behavior is in red and the neuron is in blue. The neuron. And it is really funny to see that this is also true about the brain. So for example, if I have this study that I show, this was a very famous one, that if I show a person a house and a face, and I look only at his neuron at the FFA, so I see that the neuron is very selective to faces. So it really discriminates really good between faces and houses. But the person behavior is much lower. And he has much more mistakes. So this is a really nice question in neuroscience. How could that be that our behavior is less good than the units of the brain? But now there are some more new advances regarding these questions about how they are called manifolds. Okay, manifolds. This is something new in theoretical neuroscience. So they say that this is not about the neuron alone and it's the relation and so on. I look for something about this and I'll send in the group if you're interested. But I think this is a really nice way to look at things. And here you can try also this Lord of the Ring question. And again, I think this is a really nice and easy subject. It's a bit more technical, but the idea is good. Right? Okay, so I'll talk to Sophie now regarding next week. We'll have on Sunday the mathematical reinforcement and quiz preparation on Wednesday, which practically means that we'll have 2 lessons probably to prepare for the exam. And I also sent you, again, 7 solutions, which is quite a lot for autocorrelation and cross-correlation. And now focus on the project. And if you can, try to solve the quiz. This time, I think it's a bit easier one, the recitation quiz this week. The one from Italy? Yeah. You can use everything. It's about the same course for 20 years. But I would start with Boris. Yeah. Okay. Thank you. You're welcome. You're welcome. But let me see if I really have to run to my children.
Hello, sorry. Can I ask you please again to explain how to understand ROC curves that are above a little bit?
This one?
No. The one that you used for the example.
Here.
Yes.
So
yes.
you were asking about the blue one or the red one?
I'm just asking how to interpret it.
Right. So the closer the ROC is to 1, for example, a 1 that really sits exactly here, where I'm showing with the marker, is the best. It's the most discriminative distributions, because for almost every Z, there will be almost fully discriminated, right?
Yes.
Okay. And the more I come close to the middle line, therefore I am less discriminative. So the red one, the behavior one, is less discriminative than the blue one of the neuron.
Okay, thank you.
You're welcome, Ksenia. Great. So I'll try to have a minute